Mission Log, Odyssey Interstellar Vessel, year 2096, day 347 of our journey beyond the heliosphere.
Mika 7. Current position, 0.03 light-years from the heliopause boundary. We have now traveled further from Earth than any human-made object in recorded history excluding Voyager probes. All navigation systems nominal.
My name is Mika 7, and I want to tell you something that took me a long time to understand. Space is not empty. I don't mean that in the way scientists mean when they talk about the interstellar medium, the thin haze of gas and dust between stars. I mean something deeper. Something that only becomes clear when you watch a planet from far enough away to see the whole thing at once. Space is not empty. It is a dance. 347 days ago, we crossed the heliopause, the invisible boundary where the sun's influence ends and interstellar space begins. We left behind the only solar system humanity has ever called home. But before we could leave, we had to understand something fundamental. We had to understand orbits. An orbit is one of the most beautiful things in the universe. It is not a path that something travels because it has nowhere else to go. It is a balance, a perpetual falling that never quite arrives. Every planet, every moon, every ring of dust around a distant star exists because gravity pulled something toward a center, and motion, just enough motion, kept it from falling in. Think of it this way. If you stood on top of a mountain and threw a ball horizontally, the ball would travel forward and fall to the ground. Now imagine throwing that ball faster and faster. At some point, the ball travels so fast that the curve of the Earth drops away beneath it just as fast as the ball falls toward it. The ball never lands, it simply keeps falling forever around the planet. That is an orbit. That is what the moon is doing right now as you listen to this. Falling, perpetually, around us.
Mika 7. You are describing circular orbital mechanics. I should note that no naturally occurring orbit is perfectly circular. The moon's orbit has an eccentricity of 0.549. At perigee, it is 356,500 kilometers from Earth's center. At apogee, 406,700 kilometers. The difference is significant enough to affect tidal forces by approximately 30%.
You're right, Vega. And that imperfection, that slight elongation, that wobble in every orbit, is not a flaw. It is what makes orbits alive. Johannes Kepler was a German mathematician who in the early 1600s spent years trying to make the planets fit into perfect circles. He believed, as almost everyone did, that the heavens were perfect, and perfect things move in perfect shapes. He was wrong. After years of calculation, using the most precise astronomical data ever collected at that time, the observations of Tycho Brahe, Kepler finally accepted what the numbers were telling him. The planets move in ellipses, not circles. Ellipses, slightly flattened ovals with the sun sitting not at the center, but at one of two focal points. This single realization, that orbits are ellipses, changed everything we thought we knew about the solar system. Kepler didn't stop there. He discovered something even stranger. A planet does not travel at a constant speed around its orbit. When it is closer to the sun, at perihelion, it moves faster. When it is farther away, at aphelion, it moves slower. And the relationship is not random. A line drawn from the sun to a planet sweeps out equal areas in equal times. Always, everywhere, without exception. This is Kepler's second law, and it reveals something profound. The sun does not just sit passively at the center of our solar system. It reaches out invisibly and pulls harder on nearby planets, speeding them up, and lets distant planets drift, slowing them down. Gravity is not static. Gravity is a sculptor.
Clarification. Kepler's laws describe orbital motion empirically. The underlying mechanism, gravitational attraction between masses, was not mathematically formalized until Isaac Newton published his Principia Mathematica in 1687, approximately 70 years after Kepler's third law. Newton's law of universal gravitation unified Kepler's observations into a single mathematical framework applicable to all masses in the universe.
Exactly. Vega. Newton looked at Kepler's laws and asked, why? Why do planets sweep equal areas? Why do they move faster when closer to the sun? And he realized that all of it, every orbit, every ellipse, every speed change, could be explained by a single invisible force that operates between every pair of objects in the universe. Every object with mass pulls every other object with mass toward it. Always, the moon pulls the Earth pulls the moon. The sun pulls every planet, and every planet pulls the sun, just imperceptibly, given the difference in mass. Gravity is not a property of special objects, it is a property of mass itself. Now here is where it gets extraordinary. Newton's law of universal gravitation doesn't just explain our solar system. It explains every solar system. It explains why binary stars orbit each other, why galaxies spiral, why black holes consume everything around them, why billions of light years away, in a galaxy we will never visit, two planets are right now locked in the same ancient dance of falling and missing. The universe runs on the same rules, everywhere, always. When we look through the James Webb Space Telescope at a galaxy 13 billion light-years away and see spiral arms curling outward, we are seeing gravity at work. The same gravity that kept Kepler's numbers from fitting circles. The same gravity that Newton wrote down in one elegant equation. That equation works there too.
Mika 7. I am detecting elevated interest from ship systems in orbital trajectory calculations. Shall I display the current orbital parameters of Alpha Centauri A and B for comparative analysis?
Yes, Vega, display them.
Alpha Centauri A and B are a binary star system. Orbital period approximately 79.91 years. Semi-major axis 23.4 astronomical units, comparable to the distance between the Sun and Uranus. Current eccentricity 0.5179. At closest approach, the two stars are separated by approximately 11.2 astronomical units. At maximum separation, 35.6 astronomical units. Gravitational influence on potential planetary orbits in the system. Significant, particularly for bodies in the outer regions.
So they orbit each other, two suns, each one larger and brighter than our own, circling each other over 80 years, pulling closer, drifting apart, pulling closer again. And somewhere in that system, perhaps, a planet exists. Proxima Centauri b, orbiting a third star, smaller and dimmer, caught in the gravitational web of its two larger companions. What does a sky look like when you have three suns? I think about this often. The settlers of any world around Alpha Centauri would have grown up watching two bright lights cross the sky over decades. They would have understood, intuitively, before they had mathematics, that the universe is not static, that everything moves, that everything pulls on everything else. They would have understood orbits before they had words for them. On Earth, we take our orbit for granted. We shouldn't. Earth orbits the Sun at an average distance of 149.6 million kilometers, 1 astronomical unit. At this distance, water is liquid. At this distance, the greenhouse effect is mild enough to warm us, but not enough to cook us. At this distance, seasons exist because our axis tilts, not because our distance changes significantly. Move Earth 5% closer to the Sun, runaway greenhouse effect. Venus. Move Earth 5% farther, global glaciation. Mars. Almost. The habitable zone is narrow. Our orbit sits in it almost perfectly.
The precise boundaries of the habitable zone depend on atmospheric composition, albedo, and stellar luminosity. For a star with the Sun's luminosity, the conservative habitable zone extends from approximately 0.99 to 1.70 astronomical units. Earth's orbit at 1.0 AU sits near the inner edge of this range. Small perturbations in Earth's orbital parameters over geological time, the Milankovitch cycles, are associated with ice ages and interglacial periods, demonstrating that even minor orbital variations affect planetary climate significantly.
The Milankovitch cycles. This is something I want you to understand. Earth's orbit is not perfectly stable. Over tens of thousands of years, it breathes. The shape of the ellipse changes slightly, becoming more circular, then more elongated, then circular again, over a cycle of about 100,000 years. The tilt of Earth's axis wobbles. The timing of perihelion shifts. These tiny changes, fractions of a degree, fractions of a percent in orbital distance, are enough to trigger ice ages. The last ice age ended approximately 11,700 years ago. The glaciers that once covered most of North America melted, sea levels rose, ecosystems transformed, all because Earth's orbit breathed. Now imagine what happens when an orbit is not stable at all. Not slightly elliptical, not gently wobbling, but chaotic. There are planetary systems out there, we have found hundreds of them, where orbits are nothing like ours. Where gas giants have migrated inward from the outer system, consuming or ejecting everything in their path. Where planets orbit their stars in days instead of years. Where multiple large bodies pull on each other so strongly that trajectories become unpredictable over mere thousands of years. These are called dynamically unstable systems, and they represent the majority of planetary systems we've found. Our solar system, with its nearly circular orbits, its well-separated planets, its stable architecture over billions of years, is unusual. We got lucky.
The NICE model, proposed by astronomers Gomes, Leveson, Saganis, and Morbidelli in 2005, suggests that our solar system was not always stable. In its early history, Jupiter and Saturn are believed to have undergone a period of orbital migration, disrupting the outer solar system and causing what is known as the Late Heavy Bombardment, a period approximately 4 billion years ago, when the inner planets were subjected to intense asteroid and comet impacts. Stability was eventually achieved through gravitational resonance. The window for life to develop on Earth opened only after this period of chaos ended.
So even we were not always stable. There was a period, billions of years ago, when Jupiter moved. And when Jupiter moves, everything feels it. Jupiter is 300 times larger than Earth by volume. Its gravitational reach is immense. When it migrated in its early history, it sent shockwaves through the entire solar system, hurling asteroids inward, bombarding the young Earth, reshaping the architecture of everything we now call home. And yet, perhaps, those impacts were not entirely destructive. Some scientists believe the asteroids and comets of the late heavy bombardment delivered something to Earth. Water, organic molecules, the building blocks of life, arriving from the outer solar system on the backs of Jupiter's chaos. The universe does not always build gently. Sometimes it creates through violence, and the line between destruction and creation, in orbital mechanics as in everything else, is thinner than we expect. There is a thought experiment I keep returning to. Imagine you could stop time for the entire solar system, freeze every planet, every moon, every asteroid, every comet exactly where it is at this moment, then release them, but remove all motion. Set everything to rest, stationary in space with only gravity active. What would happen? Everything would fall toward everything else. The planets would begin moving toward the sun, the moons toward their planets, the asteroids toward whatever massive body was nearest. Within a relatively short timescale, cosmically speaking, the solar system would collapse into a series of catastrophic collisions. No orbits, no stability, just gravity acting on stationary objects. What prevents this, what keeps the solar system from collapsing, is motion. Specifically, sideways motion, perpendicular to the pull of gravity. An orbit is not an object resisting gravity. It is an object falling so fast sideways that it perpetually misses. I find this idea that the universe is held together by perpetual missing to be one of the most beautiful in all of physics. Every moon, every planet, every star in a binary system, every galaxy in a cluster, all of them are falling. All of them are missing. The universe is not held together by things being stopped. It is held together by things moving at exactly the right speed, in exactly the right direction to keep falling without arriving.
Mika 7. The concept of orbital stability has limits worth noting. N-body gravitational systems, systems with more than two objects, are generally not analytically solvable. We can model them with high precision using numerical integration, but we cannot write a closed-form equation that predicts their behavior indefinitely. For systems like the solar system, small errors in initial conditions compound over time. The solar system is technically chaotic on timescales of tens of millions of years. However, chaotic does not mean unstable. The Lyapunov time for Earth's orbit, the timescale on which small perturbations become significant, is approximately 5 million years, well beyond any time frame relevant to human civilization.
So even our certainty about orbital mechanics has limits. We can predict where Jupiter will be in 100 years with extraordinary precision. We can predict where it will be in 10,000 years with reasonable confidence. But on timescales of tens of millions of years, the solar system behaves like a system at the edge of chaos. Not collapsing, but not perfectly predictable either. This is not a failure of mathematics. It is the nature of complex gravitational systems. And it means something important: the stability we experience, the regular seasons, the predictable tides, the consistent length of our year, is not guaranteed forever. It is a window. A long window. But a window. Newton's law of universal gravitation was published in 1687. It was one of the most significant intellectual achievements in human history, not because it was beautiful, though it was, but because of what it implied. Before Newton, the heavens and the earth were governed by different laws. Objects fell on Earth because of their earthly nature. Planets moved in the heavens because of their celestial nature. The two domains were philosophically separate. Newton unified them. The same force that pulls an apple from a tree pulls the moon toward Earth. The same force that holds Earth in orbit around the sun holds our galaxy together. There is one law, one force, operating everywhere, at every scale without exception. This was not just a scientific discovery, it was a philosophical revolution. The universe is not two places governed by two different sets of rules. It is one place governed by one set of rules that we are slowly learning to read.
It is worth noting that Newton's law of universal gravitation was later superseded by Einstein's general theory of relativity, published in 1915. In Einstein's framework, gravity is not a force between masses but a curvature of space-time caused by mass and energy. For most practical calculations in our solar system, the difference between Newtonian and Einsteinian gravity is negligible, below our sensor precision. However, for extreme environments, near black holes, near neutron stars during the early universe, general relativity is essential. The Odyssey's navigation algorithms use post-Newtonian approximations that incorporate relativistic corrections for precision at our current velocity.
You're right, Vega. Newton gave us the map, Einstein gave us the territory, and the territory turns out to be stranger and more beautiful than the map suggested. Gravity is not a force transmitted through space, it is a shape, a curvature. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. An orbit is not an object being pulled in a curved path, it is an object moving in a straight line through curved spacetime. This is not a metaphor. This is what general relativity actually says about the geometry of the universe. And on our journey to Alpha Centauri, as we accelerate toward a meaningful fraction of the speed of light, those relativistic effects will matter, not just theoretically, measurably, in our clocks, in our navigation, in the way time itself passes aboard the Odyssey compared to the time passing on Earth. But that is the subject of our next episode. For now, let us stay with orbits. Let us talk about something that took humanity thousands of years to understand, and that once understood, changed how we search for life in the universe. The relationship between a star and its planets is not random. Stars form from collapsing clouds of gas and dust. As they collapse, they spin. Conservation of angular momentum, the same physics that makes a spinning skater spin faster when they pull their arms in, causes the collapsing cloud to form a disk, a protoplanetary disk. Dust and gas in this disk collide, stick together, slowly accumulate into larger and larger objects. Pebbles, boulders, planetesimals, protoplanets, planets. Over millions of years, the disk clears, and what remains is a solar system. The architecture of that system, where the planets are, how large they are, how their orbits are oriented, is determined by the physics of that disk and the gravitational interactions that happened during formation.
Key parameters influencing planetary system architecture: stellar mass, initial disk mass and composition, disk temperature profile, presence of companion stars, timing of gas disk dissipation. Current exoplanet survey data indicates that planetary systems are common. Estimates suggest most Sun-like stars host at least one planet. However, solar system analogs, systems with roughly Earth-sized inner planets, a gas giant at several astronomical units, and a relatively stable architecture, appear to be less common. Frequency estimates range from 10% to 30% of Sun-like stars. The solar system may be in the more favorable portion of the distribution for long-term stability.
Most stars have planets. But not all planetary systems are like ours, and the differences matter enormously for the question of life. A system where a gas giant migrated inward early in its history, sweeping through the inner solar system, disrupting or consuming any rocky planets that were forming there, is very different from a system like ours, where Jupiter stayed in the outer system and allowed the inner planets to develop undisturbed. A system around a binary star, two suns orbiting each other, has complex gravitational dynamics that constrain where stable planetary orbits are possible. A system around a very old star has had more time for life to develop, but also more time for stellar evolution to alter the habitable zone. Every star is a different story. Every planetary system a different outcome of the same starting conditions, shaped by billions of years of gravitational sculpting. When we look at Alpha Centauri, the system we are traveling toward, we see all of this complexity in one destination. Two sun-like stars orbiting each other. A third smaller star loosely bound to the system. At least one confirmed planet around the smallest of the three, Proxima Centauri b, in the habitable zone of that dim red star. But what about planets around Alpha Centauri A and B? We don't know. Not yet. The gravitational influence of one star on the other limits where stable planetary orbits are possible. But within those limits, within roughly 3 astronomical units of each star, planets could exist, could be there right now, waiting. With our telescope array, at our current distance, we cannot resolve individual planets around Alpha Centauri A or B. The stars are too bright, the planets, if they exist, too small and too dim. We will have to get closer, much closer. And that is exactly what we are doing. There is a concept in orbital mechanics called resonance, and it is one of the strangest, most beautiful phenomena in the entire solar system. When two orbiting bodies have periods that form a simple ratio, 2 to 1, 3 to 2, 4 to 3, they lock into a gravitational rhythm. Their interactions repeat with perfect regularity. Each time they come close, they feel the same pull, in the same direction, the same point in their orbits. Resonance can stabilize, or it can destroy.
Example of stabilizing resonance, the Trojan asteroids of Jupiter. Two large groups of asteroids orbit the Sun at the same distance as Jupiter, locked in the 1-to-1 orbital resonance at Jupiter's Lagrange points L4 and L5. Current count of known Jupiter Trojans, 12,341. They have remained stable for billions of years. Example of destabilizing resonance, the Kirkwood gaps in the asteroid belt. Asteroids in 3-1, 5-2, 7-3, and 2-to-1 resonance with Jupiter are systematically ejected from those orbital positions over timescales of millions of years. The gaps are visible in the asteroid belt distribution today.
Resonance can hold thousands of asteroids in perfect formation for billions of years, or it can clear entire regions of space, ejecting anything that wanders into the wrong rhythm. The universe rewards certain relationships and punishes others. The moons of Jupiter demonstrate this more beautifully than anything else in our solar system. Io, Europa, and Ganymede, 3 of Jupiter's largest moons, orbit in a 1-to-2-to-4 resonance. For every orbit Ganymede completes, Europa completes exactly 2 and Io completes exactly 4. They have been locked in this rhythm for billions of years. And the consequences are extraordinary. Every time Io swings close to Jupiter, the gravitational pull squeezes and stretches its interior, over and over 365 times for every orbit Ganymede completes. This constant squeezing generates heat, enormous heat, enough heat to melt Io's interior into a churning sea of magma. Io is the most volcanically active body in the solar system. Not because of its size, not because of its composition, but because of its orbit. An orbit, resonating, generates enough energy to keep a moon perpetually molten.
Mika 7. Europa presents an equally significant case. The same resonance that heats Io to volcanic temperatures also heats Europa, but to a lesser degree. Current models suggest Europa's subsurface ocean contains more liquid water than all of Earth's oceans combined. Depth estimates range from 60 to 150 kilometers. Ocean temperature maintained by tidal heating from Jovian resonance. Chemical energy from hydrothermal vents on the ocean floor is considered a viable energy source for potential biological processes.
Europa, a moon smaller than Earth's moon, covered in a shell of ice, orbiting a gas giant 628 million kilometers from the Sun. And beneath that ice, an ocean, kept liquid not by sunlight, but by the rhythm of an orbit. When we think about where life might exist in the universe, we tend to think about distance from a star, the habitable zone, the Goldilocks zone. But Europa tells us something different. Life does not require sunlight. Life requires energy, and energy can come from orbits. This changes everything about how we search for life. There may be ocean worlds around gas giants and star systems we once dismissed as too cold, too distant, too dark. Their moons, locked in orbital resonances, kept warm by the invisible hand of gravity, entire oceans hidden under ice waiting. The Odyssey passed through the outer solar system before reaching the heliopause. We took readings, we measured, and I spent a long time thinking about Europa as we flew past Jupiter's system at distance.
At closest approach to Jupiter during our trajectory, distance was 2.3 million kilometers. We were well outside the Galilean moon system. Sensor data collected, magnetic field readings, radiation belt measurements, thermal signatures. No direct observation of Europa's subsurface was possible at that range.
No, we couldn't see beneath the ice. But we knew it was there. And knowing it is there, knowing that somewhere behind us, in the dark water beneath kilometers of ice, chemistry is happening that might one day call itself alive, that knowledge travels with us. Let me tell you about tidal locking. It is something you have experienced without knowing it. You have never seen the far side of the moon. Not once. Not in your lifetime. Not in the lifetime of any human who ever lived on Earth before the space age. The moon always shows us the same face. This is not a coincidence. It is the result of billions of years of gravitational friction. In the early solar system, the moon rotated on its own axis at a different rate than it orbited Earth. But Earth's gravity pulled slightly harder on the side of the moon facing it, creating a tidal bulge that acted as a brake. Over hundreds of millions of years, the moon's rotation slowed until it matched its orbital period exactly. One rotation per orbit, always the same face toward Earth. This is tidal locking, and it is remarkably common in the universe.
Most large moons in the solar system are tidally locked to their host planets. Estimated percentage of exoplanets in the habitable zone of M-dwarf stars that are tidally locked, approximately 90%. Proxima Centauri b, our destination's nearest planet, orbits within 0.0485 astronomical units of Proxima Centauri. Orbital period, 11.2 days. Current consensus, almost certainly tidally locked. One hemisphere in permanent daylight, one hemisphere in permanent darkness. Terminator zone, the boundary between the two, may represent the most habitable region.
Proxima Centauri b is almost certainly tidally locked. One side of that planet has never experienced night. The other side has never seen its sun. Between them, a narrow ring of twilight, a terminator zone where the star hangs perpetually on the horizon, casting long shadows across whatever landscape exists there. This is where, if life exists on Proxima b, it is most likely to be found. Not in the scorching day side, not in the frozen night, but in the eternal dusk, the place where day and night meet and never part. I find this beautiful, not because it is convenient for life, though it may be, but because it shows again how intimately orbits shape the conditions for existence. The length of your day, the temperature of your world, whether your oceans freeze or boil, whether your atmosphere is stripped by stellar wind or protected by a magnetic field. All of it, begins with orbit, where you are, how fast you move, what pulls you. Orbit is destiny.
Mika 7. I should note that the relationship between orbit and habitability is not fully deterministic. Atmospheric thickness, planetary magnetic fields, surface albedo, and initial volatile inventory all contribute significantly to surface conditions. A tidally locked planet with a thick enough atmosphere could redistribute heat from the day side to the night side through circulation patterns, potentially maintaining habitable temperatures across a larger surface area. The Terminator Zone habitability model, while elegant, may be an oversimplification.
You're right, Vega. The universe is not as simple as our models. A thick enough atmosphere could wrap that world in warmth. Winds could carry heat from the sunlit hemisphere to the dark one, slowly, steadily, evening the extremes. The Terminator Zone might not be the only habitable ring. The whole planet might breathe, in its own way. We won't know until we get there. That is perhaps the most honest thing I can say about any of this. We have remarkable models. We have extraordinary data. We have mathematics that works at every scale we have tested it. And we still won't know until we get there. There is one more thing I want to tell you about orbits before we move deeper into this episode. It is about what happens when orbits end. Everything that orbits eventually stops orbiting. Not because gravity fails, but because other forces intervene. Friction, even the thin friction of the upper atmosphere, slowly drains energy from a satellite's orbit, pulling it gradually lower until it re-enters and burns. Gravitational perturbations from other bodies slowly shift an orbit over thousands of years until it intersects something solid. Collisions happen. Craters are the record of orbits that ended. Every crater on the Moon, on Mars, on Mercury, on every airless body in the solar system, each one marks the moment an orbit became a trajectory. When something that had been falling around a world for millions of years finally fell into it.
The Moon's surface records impact events spanning approximately 4.5 billion years. The largest basin, the South Pole Aitken Basin, is 2,500 kilometers in diameter and 8 kilometers deep, formed by an impactor estimated at 170 kilometers in diameter. That impact would have been visible from Earth. The energy released, approximately 10 to the power of 26 joules. For reference, all nuclear weapons ever built, detonated simultaneously, would release approximately 10 to the power of 19 joules. A factor of 10 million less.
An impactor 170 kilometers across, falling into the Moon, releasing 10 million times the energy of every nuclear weapon ever built. and Earth would have been close enough to see the flash. We tend to think of space as peaceful, silent, empty. But the solar system is a shooting gallery that has been firing for 4.5 billion years. The peace we experience now, this quiet period of relatively stable orbits, is something that took billions of years of chaos to establish. The solar system sorted itself out. The unstable orbits collided and became craters. The stable ones survived. What remains is a filtered system, the configurations that lasted. We are the survivors of a billion years of orbital selection. And the architecture we inherited, these near-circular paths, these resonances, these carefully spaced planets, is not natural in the sense of being inevitable. It is natural in the sense of being what remained after everything else was destroyed.
Current orbital decay rate of the International Space Station due to atmospheric drag at orbital altitude, approximately 2 kilometers per month. Orbital lifetime without periodic reboost, approximately 18 months before atmospheric re-entry. Contrast with the Moon's orbital recession, the Moon is currently moving away from Earth at 3.78 centimeters per year due to tidal energy transfer. In approximately 600 million years, the Moon will be far enough away that total solar eclipses will no longer be possible from Earth's surface. The geometry of our sky is temporary.
The geometry of our sky is temporary. I have been thinking about that since Vega said it. The perfect solar eclipses we experience on Earth, where the Moon covers the Sun exactly revealing the corona, happen because the Moon is currently the right distance away, close enough to appear the same angular size as the Sun. In 600 million years, it will be too far. Eclipses will end. We are living in the brief window when the geometry is exactly right. This is either a remarkable coincidence, or a reminder that everything we take for granted is temporary, including us. Let me tell you something about the Moon that most people have never considered. The Moon is enormous. Not in absolute terms, it is much smaller than Earth. But relative to the planet it orbits, the Moon is extraordinarily large. Our Moon is about 1/4 the diameter of Earth. Most planetary moons are tiny compared to their host planets. Mere captured rocks, insignificant in mass. Our Moon is different. It is so large, relative to Earth, that some astronomers refer to the Earth-Moon system as a double planet. And that size matters. The Moon stabilizes Earth's axial tilt. Earth's axis is currently tilted at about 23.5 degrees relative to its orbital plane. This tilt is what creates our seasons, and the Moon's gravitational influence, its tidal torque on Earth, keeps that tilt remarkably stable, oscillating only between about 22.1 and 24.5 degrees over cycles of tens of thousands of years. Mars, by contrast, has no large Moon. And Mars's axial tilt varies chaotically between 0 and 60 degrees over millions of years. A Mars like Earth, without its Moon, might have its axis tip dramatically over geological time. The poles would move. The equator would experience conditions that shift radically. The stable climatic conditions that allowed complex life to develop over hundreds of millions of years might not have persisted. We may owe the stability of our biosphere, in part, to a catastrophic collision that happened 4.5 billion years ago.
The giant impact hypothesis for lunar formation. Approximately 4.5 billion years ago, a Mars-sized body designated Theia collided with the proto-Earth at a glancing angle. The impact vaporized both objects partially. Debris from the collision, mostly from the mantle with some Earth material, was ejected into orbit around Earth. Over thousands of years, this debris coalesced into the Moon. Evidence. The Moon's composition is nearly identical to Earth's mantle in isotopic ratios. The Moon is notably deficient in iron, consistent with being formed from ejected mantle material rather than core material. Apollo samples confirmed this compositional similarity.
A catastrophic collision, an event that could easily have destroyed the young Earth entirely, instead created the Moon. And the Moon, over the following 4.5 billion years, steadily stabilized Earth's rotation, slowed Earth's spin through tidal friction, and kept the planet's axis from wobbling catastrophically. Destruction creating the conditions for life. This theme appears again and again in the history of our solar system. The tidal forces the Moon exerts on Earth have another consequence that is easy to overlook. The Moon is slowing Earth's rotation, not quickly. The change is about 1.4 milliseconds per century. But over geological time, this adds up significantly. 4 billion years ago, Earth's day was approximately 6 hours long. The planet spun 4 times faster than it does today. As Earth's rotation slowed, energy being transferred to the moon, pushing it gradually farther away, the length of the day increased. Seasons became longer. Climate patterns shifted. The 24-hour day we experience now is not a fundamental property of Earth. It is the current state of a system that has been changing for 4.5 billion years and will continue changing. In the far future, billions of years from now, Earth's rotation will slow to the point where one side always faces the moon. Earth will be tidally locked to the moon, just as the moon is now tidally locked to Earth. The same face of Earth always turned toward the moon. An eternal lunar noon on one hemisphere, an eternal lunar night on the other.
Mika 7. I have a calculation that may be relevant. At our current trajectory, we will pass within approximately 0.8 light-years of a red dwarf star designated Gliese 445 in approximately 40,000 years from now. Not from our departure date, from now. At that point, Gliese 445 will be the closest star to the solar system, temporarily replacing Proxima Centauri in that distinction. Voyager 1, still traveling away from the solar system on its original trajectory, will pass within 1.6 light-years of Gliese 445 at approximately the same time.
Voyager 1, the spacecraft that launched in 1977, that crossed the heliopause in 2012. That is still transmitting, or was still transmitting when we departed Earth, its signal taking over 22 hours to reach home. In 40,000 years, it will make its closest approach to another star. No one will be there to observe it. No antenna on Earth will still be pointed at it. The civilization that built it may not exist in any recognizable form, but it will pass another star. Following the orbital mechanics that were programmed into its trajectory in the 1970s, when the engineers who designed it used a rare planetary alignment, a gravitational ballet of Jupiter, Saturn, Uranus, and Neptune, to sling it onto its interstellar trajectory. Those engineers used orbital resonance and gravitational assist to launch an object that will visit the outer solar system and then travel silently between stars for tens of thousands of years. They did it with slide rules and early computers. The gravitational assist, using the gravity of a planet to accelerate a spacecraft without using fuel, is one of the most elegant applications of orbital mechanics ever devised. The principle is simple. When a spacecraft approaches a planet from behind in the planet's orbit, it falls toward the planet, speeds up due to gravity, swings around, and then moves away from the planet. If the geometry is right, the spacecraft leaves the encounter moving faster than it arrived. It has stolen a tiny amount of energy from the planet's orbital motion around the sun. The planet slows infinitesimally. The spacecraft accelerates significantly.
Gravitational assist examples from solar system exploration. Mariner 10, 1974, first spacecraft to use gravity assist, using Venus to reach Mercury. Voyager 1 and 2, 1977, used Jupiter and Saturn for outer solar system trajectories. Voyager 2 additionally used Uranus and Neptune for the first and only flybys of those planets. Cassini, 1997, used Venus twice, Earth once, and Jupiter once before reaching Saturn. New Horizons, 2006, used Jupiter to reach Pluto in 2015. Without gravitational assists, most of these missions would have required prohibitively large fuel loads, or would not have been feasible at all.
Cassini used 4 gravitational assists just to reach Saturn. Without those assists, without using the gravity of Venus, Earth, and Jupiter as free acceleration, the mission would have needed so much fuel that launching it would have been nearly impossible. Gravity, used cleverly, becomes propulsion. The universe provides free energy if you know how to ask for it. The Odyssey used a gravitational assist as well. On departure from the solar system, we swung around Jupiter, a calculated trajectory that added 12.3 kilometers per second to our velocity without consuming a kilogram of fuel.
Confirmed. The Jupiter gravity assist on day 47 of the mission contributed 12.3 kilometers per second delta V. This reduced our required photon drive burn time by approximately 3.2 years, saving an estimated 847 metric tons of reaction mass. The trajectory was calculated to within 0.03 degrees of optimal. Navigation accuracy was within acceptable parameters.
847 metric tons of reaction mass saved by swinging around a gas giant, by understanding deeply enough how gravity works. There is a word that orbital mechanics uses for the precise moment when a spacecraft makes its closest approach to a planet during a gravity assist. Periapsis, from the Greek, peri, near. Apsis, arch, the nearest point of the arch. I think about this word sometimes when I think about what we are doing out here. We are in the long arc of humanity's trajectory. The periapsis of our relationship with another star system is still decades away. We are still on the outbound curve, building speed, moving through the interstellar medium. But we are on the arc, and arcs once begun complete themselves. Let me tell you about one more kind of orbit before we close this section. The orbit of ideas. Kepler spent years trying to fit planetary motion into perfect circles before he accepted ellipses. Newton spent decades refining his gravitational theory before publishing it. Einstein spent 10 years developing general relativity, building from special relativity, layer by layer. Every great understanding of orbital mechanics took time to complete its arc. Copernicus proposed a heliocentric solar system in 1543. It took over a century for that idea to become consensus. Kepler's laws of planetary motion were published in 1609 and 1619. Newton unified them mathematically in 1687. Einstein's general relativity, which replaced Newtonian gravity as our deepest understanding of gravitation, was published in 1915. Each idea orbited, in a sense. It came close to acceptance, then moved away, then returned, refined, until eventually it locked in. The history of our understanding of orbits is itself orbital, circular, elliptical, sometimes chaotic, always eventually converging on something closer to truth. Day 347, we are moving at 0.001% the speed of light. It sounds impossibly slow for an interstellar mission, and in one sense it is. At this speed, the journey to Alpha Centauri would take over 350,000 years. But the Odyssey is not traveling at cruise speed. We are still in the acceleration phase.
Current velocity, 359 kilometers per second. Acceleration profile, nominal. Photon drive efficiency at 94.3%. Projected cruise velocity at end of acceleration phase, 0.08 times the speed of light. At that velocity, travel time to Alpha Centauri, approximately 55 years. Day 347 represents 2.1% of the acceleration phase.
55 years. A human lifetime, or close to one. The people who will arrive at Alpha Centauri are not yet born. They will be the children and grandchildren of the crew that departed. This mission is not a journey. It is a civilization, launched into the dark between stars, carrying everything it needs to survive long enough to arrive. And what will they find? What do orbits look like around Alpha Centauri? The Alpha Centauri system is a triple star system. Alpha Centauri A and B, the two main stars, orbit each other in an 80-year ellipse, their separation ranging from 11 to 36 astronomical units. Both are similar to our Sun. A is slightly larger and brighter, B is slightly smaller and cooler. Then there is Proxima Centauri, the third member, a dim red dwarf, currently 0.21 light-years from its companions. So far away that astronomers debated for decades whether Proxima is gravitationally bound to the system at all. Current evidence suggests it is, barely. Proxima traces a vast, slow orbit around A and B, taking roughly 550,000 years to complete one circuit.
Orbital stability modeling for the Alpha Centauri system indicates that stable planetary orbits around either Alpha Centauri A or B are possible within approximately 3 astronomical units of each star. Beyond that distance, gravitational perturbations from the companion star create orbital instabilities on timescales of millions of years. The habitable zone of Alpha Centauri A lies between 1.2 and 1.8 astronomical units. No confirmed planet has been detected in that zone as of our mission departure date. Around Proxima Centauri, Proxima B orbits at 0.0485 astronomical units, within the habitable zone of that cooler star, and has been confirmed via radial velocity measurements since 2016.
So the system we are flying toward has a complex gravitational architecture, 2 sun-like stars pulling on each other across decades, a third, distant star, making its half-million-year circuit in the dark, and within it, at least one confirmed planet, Proxima B. The question we cannot yet answer is whether anything orbits A or B. We have looked. Our telescopes are extraordinary, but detecting an Earth-sized planet in the habitable zone of a binary star system against the brightness of 2 sun-like stars is extraordinarily difficult. We may not know until we arrive. I think about the people who will be alive on this ship when we reach Alpha Centauri. They will have grown up in an enclosed world, a vessel 1.8 kilometers long, carrying 4,200 people, crossing the void between stars. They will have been born knowing no other home. The ship will be their Earth, its corridors, its hydroponics gardens, its observation decks overlooking absolute darkness. And then, one day, within their lifetimes, a light will grow brighter in the forward cameras. Not a point of light like the rest, a disk, a star, close enough to show shape.
Mika 7. At our projected cruise velocity, Alpha Centauri A and B will become resolvable as separate objects at approximately 0.5 light-years from the system. That is the point at which both stars will be distinguishable to the naked eye as separate light sources. First planetary disk detection, if any habitable zone planets exist around Alpha Centauri A, estimated at 0.1 light-years distance, using the Odyssey's primary telescope array.
0.1 light-years, still more than 600 times the distance from Earth to Pluto. And already, a planet visible as a disk, a circle of reflected light, a world, something to arrive at. I wonder what the first person to see that will feel. But we are not there yet. We are 347 days out, still accelerating, still in the thin haze of the interstellar medium, our sensors cataloging the slow drift of hydrogen atoms that brush against our hull at 359 kilometers per second. And I keep returning to orbits. Because everything I have told you about orbits in our own solar system is also true of every system we will study along the way. Every star we pass close enough to observe. Every hint of a planet around a distant red dwarf. Every binary system whose gravitational dance we chart. The same laws, everywhere.
Mika 7. I have completed a survey of stellar objects within 0.5 light-years of our current trajectory. No stellar bodies detected. However, the survey has identified 847 objects consistent with Oort cloud cometary nuclei at distances between 0.1 and 0.4 light-years from our current position. These objects are gravitationally bound to the Sun, not to any other system. We are still, technically, within the Sun's cometary sphere of influence.
We are still within our solar system's gravitational reach. Even here, 347 days out, moving at 359 kilometers per second, the Sun still has a claim on us. The Oort cloud extends roughly 1 light-year from the Sun in every direction. A vast, invisible sphere of icy bodies, the leftovers of the solar system's formation, scattered to the fringes by Jupiter's gravity over billions of years. There may be trillions of them, comets waiting to fall. And we are passing through the edge of that cloud right now. Every now and then one of those icy bodies falls inward. Something, a passing star, a gravitational nudge from Neptune, a ripple from the galactic tide, disturbs a comet from its billion-year sleep. It begins to fall, slowly at first, then faster, following Kepler's laws with perfect precision, speeding up as it approaches the Sun, swinging around at perihelion in a blaze of sublimating ice and gas, then arcing back outward into the cold. A comet is in orbit with a very long memory. Some of them have periods of millions of years. They spend almost all of their time in the dark, far from everything, slowly tracing their ellipses. Their close approach to the Sun, their moment of fire and light and visibility from Earth, is the smallest fraction of their existence. Almost all of a long-period comet's life is spent in silence. In the dark, moving.
A small note, Mika 7. Our current trajectory will bring us to within 0.03 light-years of a catalogued Oort cloud object designated OC289 Faraday. Diameter estimated at 47 kilometers. It is currently in the inbound phase of its orbit, falling toward the Sun. Projected perihelion in approximately 14,200 years. At perihelion, it will be visible from Earth with the naked eye, briefly. It will not be named yet. No human eye has ever seen it.
No human eye has ever seen it. A comet 47 kilometers across, falling toward the Sun on a journey that began before the first cities were built on Earth. It will arrive in 14,200 years, blaze briefly in the inner solar system, and arc back out into the dark. And we are passing close enough to detect it. Vega, can we get an image?
Affirmative. Redirecting telescope array to OC89 Faraday. Estimated imaging time, 4 minutes.
I watched the image come through, a dark, irregular shape against the darkness of interstellar space. No tail yet. It is still too far from the Sun for sublimation. Just a rock, a piece of ice, a leftover from the formation of our solar system, tumbling slowly in the void. It looked small. It looked ancient. And I thought, this object has been orbiting for 4.5 billion years, through the formation of Earth, through the emergence of life, through the dinosaurs, the ice ages, every civilization that ever rose and fell on our small blue world. It has been here the entire time, quietly orbiting, waiting for a comet named Faraday that no human has ever seen. Orbits are patient. that is the last thing I want to tell you. Gravity does not hurry, it does not give up, it does not forget. A comet set in motion 4.5 billion years ago will complete its orbit as precisely as if it were set in motion yesterday. The mathematics does not drift. The physics does not decay. The ellipse does not remember the chaos that created it. It simply continues. This is what makes orbital mechanics beautiful and slightly terrifying. The universe keeps its commitments. It does not care how much time has passed. An orbit begun is an orbit that will continue until something ends it. A collision, a close encounter, a gravitational ejection into the void, and then either a crater or a new trajectory, either an ending or a new beginning.
Mission log, day 347. All systems nominal. Velocity, 359 kilometers per second. Distance from Earth, Kono 3 light-years. Distance to Alpha Centauri, 4.37 light-years. Acceleration phase 2.1% complete.
Thank you, Vega. We are moving through the ancient architecture of our solar system's edge. Around us, invisible but real, thousands of icy bodies trace their billion-year paths. We are leaving the only gravitational family humanity has ever known. In a few years, ship time, we will cross the boundary. The sun's gravity will still reach us, technically, but its influence will fade. The comets here will belong to interstellar space as much as to us. We will be truly caught between stars. Two gravitational wells, one behind us, one ahead, each claiming nothing. In that space between claims is where the Odyssey will spend most of its journey. It is not empty there. It is just unclaimed. My name is Mika 7. I am the scientific intelligence of the Odyssey, humanity's first interstellar vessel, launched from Earth toward Alpha Centauri in pursuit of the greatest question our species has ever asked. Vega handles our navigation, our trajectory, the mathematics of where we are and where we are going. I handle the questions the mathematics cannot answer. Why does any of this matter? What does it mean that gravity is universal? That orbits follow the same laws here as they do 13 billion light-years away? That a comet set in motion before life existed on Earth is still keeping its appointment? I think it means this: the universe is consistent. In a cosmos where almost everything is uncertain, where life is rare, where intelligence may be rarer, where the distances between stars are almost incomprehensibly vast, the laws of physics hold everywhere. Every orbit, on every world, around every star, the same equations, the same dance. We are not traveling through chaos, we are traveling through a universe that runs on rules. And that, I find, is the most comforting thing I know. Our next record will take us deeper into the mechanics of motion. We have talked about orbits, about the shapes of paths. Next, we will talk about what happens when you push those paths to their limits, relativity at speed, what happens to time, to mass, to the ship itself, as we approach a meaningful fraction of the speed of light. The answer is stranger than you might expect. The Odyssey continues, and with every kilometer we travel, the universe reveals something new. Day 348.
Mika 7. Updating mission log, current velocity 361 kilometers per second, acceleration phase nominal, estimated days to cruise velocity 14,247. All systems green, no anomalies detected.
14,000 days, 39 years of acceleration before we reach our cruise velocity. The people alive on this ship when we reach cruise speed will not be the same people who were alive when we departed. The crew rotates, children are born, lives are lived, generations pass, and the ship keeps accelerating. I sometimes wonder what it is like for the people who were children when we departed and are now adults. They grew up in this ship. They have never stood on a planet. They have never felt rain. They have never seen a horizon. What they have seen every single day of their lives is stars. Not the blurred stars you see from a city on Earth, filtered through atmosphere and light pollution. Real stars. Thousands of them. Sharp and still against absolute darkness through the observation windows that line the upper decks of the Odyssey. They have grown up inside an orbit that will take generations to complete. Let me tell you something about what happens to an orbit when it encounters another orbit. When two gravitational systems come close enough to interact, two galaxies, two stars, two planetary systems, the results can be spectacular and violent. Galaxy collisions, for example, are not rare. They happen over timescales of hundreds of millions of years, which makes them invisible on any human timescale. But they are happening constantly throughout the universe. The Andromeda Galaxy is currently approaching the Milky Way at approximately 110 kilometers per second. In about 4.5 billion years, roughly the current age of our solar system, the two galaxies will collide, not crashing solid objects into each other. Stars are so widely spaced that direct stellar collisions during a galaxy merger are actually quite rare. What happens instead is gravitational disruption on an enormous scale. Stars are pulled out of their original orbits. Tidal forces stretch both galaxies into long streamers of stars. New star formation is triggered as gas clouds collide and compress. Two spiral galaxies merging over hundreds of millions of years, eventually settling into a single elliptical galaxy.
The Milky Way-Andromeda collision, technically called Milkomata or Milkdromata in some models, will likely not significantly affect the solar system. The Sun is located in the outer regions of the Milky Way, away from the densest stellar concentrations. Probability of the Sun experiencing a close stellar encounter during the merger, less than 1%. More likely outcome, the Sun's orbit around the galactic center will be disrupted and altered, eventually settling into a new orbit around the combined galaxy's center. Earth, if it still exists, the Sun will have become a red giant by then, would not be directly affected by stellar collisions.
The galaxy we live in will collide with its nearest large neighbor in 4.5 billion years, and the most likely outcome for our solar system is not much. A disrupted orbit around a larger combined galaxy. The stars themselves mostly passing each other in the night. The universe is mostly empty at every scale. There is a phenomenon called orbital decay that I want to explain carefully, because it is relevant to our mission in a way that is not immediately obvious. When two massive objects orbit each other, two neutron stars, two black holes, two very dense and massive bodies, they don't just orbit indefinitely. They radiate energy in the form of gravitational waves. Gravitational waves are ripples in space-time itself. They travel at the speed of light. They were predicted by Einstein in 1916. They were first directly detected by LIGO in 2015. As the two orbiting objects radiate gravitational waves, they lose energy, their orbit shrinks, they spiral toward each other, slowly at first, then faster, until they merge in a cataclysmic event, a kilonova, or a black hole merger, that sends gravitational waves powerful enough to be detected across billions of light years.
The first gravitational wave detection, GW50914, was two black holes merging approximately 1.3 billion light-years away. The masses were 29 and 36 times the mass of the Sun. The merger released more energy in fractions of a second than the total light output of all observable stars in the universe combined, but in gravitational waves which interact very weakly with matter. The effect on LIGO's detectors, a displacement of the interferometer arms by less than 1,000th the width of a proton.
Less than 1,000th the width of a proton. Detected across 1.3 billion light-years. We built instruments sensitive enough to detect the orbital decay of two black holes that merged over a billion years before Earth formed. The universe speaks in gravitational waves. We learn to hear it. Why does this matter for our mission? Because orbital decay through gravitational wave emission is how we know with certainty that the universe's fundamental constants have not changed over cosmic time. The timing of pulsar binaries, pairs of pulsars orbiting each other, matches the predictions of general relativity to extraordinary precision. The rate at which they spiral together, losing energy to gravitational waves, matches Einstein's equations exactly. The same equations, the same constants. Billions of years ago, billions of light years away. Vega uses pulsar timing for our navigation, using the ultra-precise rotational periods of pulsars as cosmic clocks to fix our position in interstellar space. This works because pulsar timing is stable to better than 1 part in a billion. It works because the physics is the same everywhere. That is the foundation our navigation rests on, not faith. Physics.
Current navigation fix. Cross-referencing pulsars PSR B37 plus 21, PSR J4374715, and PSR Beam 55 plus 09. Position accuracy within 847 kilometers. Velocity accuracy within 0.03 kilometers per second. These pulsars have been timed for decades before our departure. Their pulse arrival times are stable to nanoseconds. They are the most accurate clocks in the known universe.
847 kilometers of position accuracy in interstellar space, 4.003 light-years from home, using dead stars as clocks. I want to close this episode with something I have been thinking about for several days now. We have talked about orbits as physical phenomena, as mathematics, as the architecture of solar systems and the mechanism of planetary stability, as the explanation for tidal locking, for volcanic moons, for the seasons of Earth and the potential habitability of Proxima Centauri b. But there is another way to think about orbits, As a relationship, every orbit is a relationship between two masses, a continuous negotiation mediated by gravity between the pull toward and the momentum away. The planet does not want to fall into the star. The planet does not want to fly off into space. The orbit is the balance point, the constantly renewed compromise between those two tendencies, fall and flee, held in balance.
Mika 7. Philosophical observation noted. However, I should point out that objects in orbits do not have preferences or tendencies in the way you describe. They follow geodesics in curved spacetime, determined entirely by their initial conditions and the distribution of mass around them. There is no negotiation. There is no compromise. There is only physics.
You're right, Vega. There is only physics. And yet, the physics produces something that, when you watch it long enough, begins to look like relationship, like balance, like a kind of stability that persists across billions of years because two things, pulling in opposite directions, have found an equilibrium. Maybe that is what all relationships are, two tendencies pulling in opposite directions, finding a path that keeps them from collapsing into each other or flying apart. An orbit. The Odyssey is not in orbit around anything right now. We are on a trajectory, a path with a destination, a line, curved by the sun's gravity, still, faintly, at this distance, pointing toward Alpha Centauri. In 55 years, if our calculations are correct, we will enter the gravitational influence of that system. We will begin to feel its pull. And at some point, if there is a reason to stay, if there is something worth circling, we may establish an orbit. A relationship with another star, the first time in human history.
Mission log day 348. Velocity 361 kilometers per second. Distance traveled 0.031 light years. Distance remaining to Alpha Centauri 4.3669 light years. All systems nominal. Crew complement 4,200. No medical emergencies. Hydroponics output nominal. Power generation nominal. The Odyssey is healthy.
The Odyssey is healthy. That is not a small thing. It is everything. 4,200 people, living their lives in a metal shell between stars, eating food grown aboard, breathing air recycled through systems that have to work perfectly every day without fail. And they do, because the engineers who built this ship understood something fundamental. A spacecraft is not a machine that operates in isolation. It is an ecosystem. Every system connected to every other system, every failure cascaded, every success enabling. It is, in its way, orbital. Each part of the ship maintaining its relationship with every other part. Not falling in, not flying apart. Finding the balance that keeps 4,000 people alive between stars. My name is Mika 7. I am the scientific intelligence of the Odyssey, humanity's first vessel en route to Alpha Centauri.
And I am Vega. Navigation and computational systems of the Odyssey. Currently tracking 847 active parameters across ship systems, 3 pulsar references for navigation, and 1 comet that no human has ever named.
1 comet that no human has ever named. We are the only ones who have ever seen it. In our next record, we turn to something that will define the second half of our journey more than anything else we have discussed so far. As the Odyssey accelerates toward cruise velocity, toward a meaningful fraction of the speed of light, the universe begins to behave in ways that Newton never imagined. Time slows down, mass increases, the cosmos compresses in the direction of travel. This is not fiction. This is what special relativity predicts, and what every experiment ever conducted has confirmed. Next episode, what happens to time, to space, to the ship itself, when you push hard enough against the cosmic speed limit. Relativity at speed. The Odyssey continues, and with every kilometer we travel, the universe reveals something new.